So hi everybody, and this is the name of my project. The main objective is to introduce a parallelized packet parsing architecture in the wireless network card driver to reduce the latency and enhance the overall network throughput. And this is my outline. Regarding the background, let's start with the basic overview of computer network and the network cards are typically divided into four layers. In some of those, they are implemented in software, while others are handled by hardware. The hardware components correspond to the data link layer and the physical layer, which align with the device controller and driver in the operating system. The software are those above the kernel space. So in reality, hardware delays really determine most of our network latency. And besides, Wi-Fi also have a more security problem due to some weakness on standard compared to the Ethernet. So because of that, I've choose to look in how to make Wi-Fi driver better. So in the Wi-Fi driver at the data link layer, it basically designed using AO 2.11 protocol. The main thing to know here are three types of package. And the first is the management packet. These are just for managing Wi-Fi connection. And the second one is control packet. In the environment with multiple Wi-Fi device, this package is used to prevent collision and manage communication between them. And the third one is data package. These are just the regular network data. Okay, so here is about Wi-Fi driver design for most of the network card provider. So as you can see, when a package is received by hardware, it first goes through the physical layer parsing, and after that, it's sent via PCIe or USB channel to the host machine for data link layer parsing. And finally, it passes up to the relevant higher layer protocol in the kernel for further parsing. The key thing here is that each box represents a thread, and each thread only calls the next thread to run after making sure that the previous one has completely finished. The design is extremely inefficient and leads to a following problem. First, for type 2 data frame, they are limited by the slowest package parting thread. Even as Wi-Fi driver get better and better, the latency bottleneck still gets stuck here, so we cannot fully utilizing high bandwidth capability. As for the Type 0 management frame, they are susceptible to package forgery, which can lead to package congestion. Any attacker can use like denial of service to effectively freeze the driver by sending a lot of invalid packets in the air. So after identifying this issue, my project aims to solve them by introducing parallelized data flow in the Wi-Fi driver. Regarding the parallelized data flow, I've actually done research across 3 papers and 1 standard. Because once the data turn into the network package, the order will be super important. If they arrive out of sequence, other protocol in the kernel will have to reorder them, which of course takes extra time. So how to slightly sacrifice order but still boost throughput? That's a key area of the study. It is called the cross-layer performance trade-off analysis. So because of the time limit, I have to skip straight up to the conclusion. The conclusion is that we can increase the throughput if the out of order rate is less than 5%. Another way to put it is avoid triggering the function on the top protocol called fast retransmission, or ensure that the package reordering delay is less than the round trip time. And the next research is security issue with the type 0 management frame. Among this, the deauthentication attack is the most famous. It works by continuously sending fake packets to disconnect our device, makes them completely unable to connect, which is the type of denial of service. So regarding the deauthentication attack related research, I found about 3 papers. To put it simple, those R3 pairs are using machine learning model, such as SVM or random forest, or the distribution function to normalize the model to differentiate the package or the network traffic. And those papers all have their drawback. They claim to be the intrusion detect system, but they still need to copy package from the kernel space to the user space for filtering, and then copy the valid package back to the kernel space, which lead to the tons of latency. And besides, the model themselves have their limitations, such as it's not applicable to every package that made by attacker. So to address this issue with the data package and management package, I designed a parallelized load balancing data flow to solve both the blocking and latency problem, which caused by the synchronized design. For the data package, I add additional data flow and implemented round-robin scheduling, which is a scheduling algorithm for a lot of processes in the OS to alternatively run by CPU. And this makes the time package are sent into the OS much more consistent. Besides improving the throughput by using more thread, it also helps reduce the jitter between the packets. Next is the security issue with the management package. What I've done here is separate the management packet from data and control package first. Then I inspect this management package in the parallel. This means I can prevent the attacker from exploiting this vulnerability to launch attack on parsing thread. Okay, so this is the original packet flow in the detail. Each box represents a thread. It involves two types of synchronization. One is the hardware synchronization on the left-hand side, which is between the network card and the host machine. The other is software synchronization within the host itself, meaning thread synchronization, and that has blocking issue. Uh, for the type 2 data package, I've added extra thread, and around the package parsing process 2, I implement the lock-free queue before and after this that the thread parse packet asynchronously. So let's start with the first step. After a packet finishes a parsing one, I use sequence number divided by 2 to alternatively place it into the queue of this two thread. And this two thread parallel parsing essentially do the same thing. And finally, I use the round robin scheduling to access this queue alternatively and then pass it to the upper protocol. So since my time is limited, I can only give a quick overview of the round robin concept. In a simple term, it's an algorithm managed by the operating system that allows multiple processes to take turn using CPU, each for a small fixed amount of time. This ensures that CPU cycle through every process. Now regarding to the management package, my main approach is to use series of filtering mechanisms to handle the authentication attack on the specific environment. First, during the parsing stage 1, we just talked about, I divert management package into the parallel thread. Then I capture all the information and data from the management package. Among the management package, the authentication package are one among it. When I receive the authentication package, I'll check its transmission frequency. If it shows up too many times within a second or a time slot, I will mark it as an attack package. In that case, all packages within that second or time slot will be discarded. And next, regarding those management packages we are just discussing, all management package information that enter the thread will be recorded. For example, I record the receive signal strength indicator, which reflects the distance between the Wi-Fi hotspot and the device. When the authentication package is received, I will have that package RSSI to compare with the RSSI of historical management package. If it exceeds one standard deviation, the authentication package will be discarded. And finally, I would check the sequence number because management packages are used an incrementing sequence number by implementing circular array. But the attacker will never know the current sequence number making it harder for them to forge the package effectively. Okay, so this is my experiment setup. First, I will demonstrate that parallel data flow can increase the throughput in an environment without any attack. And next, I will transmit data while the attack is sending a invalid package at the same time to observe the final impact. And this is the original data flow we just discussed. And I'm also using the improved model, which is the simple single producer and consumer model. I just insert the two buffer between the threads for better cushioning. Here are the quantified results. I run each architecture for 8 hours. And you can see that throughput barely changed, and the RTT actually slowed down due to the extra buffer design. However, on the other hand, because of the asynchronous design, although the throughput barely changed, but the jitter of throughput improved significantly, which means that the throughput, the data transmit the data, um, not fluctuate a lot. And next, I compare the multiple producer and consumer model data flow architecture with the original design. So as you can see, all metrics have improved, and throughput increased by about 10%, and RTT was significantly reduced, and jitter also decreased. And next is the experiment under the attack. The column from left to the right represent the original architecture under attack and the original architecture without attack, and then is the modified one. When the original architecture is under attack, we can see that throughput drop about 30%. So do other metric. The modified architecture still maintain about 95% of the performance. And then it's about round trip time. Original architecture saw the RTT increased by about 5 times compared to no attack. The modified architecture, on the other hand, only experienced an increase of about 1%, 1.3 times. And this is my final contribution. First is to reduce the latency by using the parallel data flow parsing. And the second is to reduce if I reduce the latency, can indirectly lead to increase the throughput. Third, compared to the existing intrusion detect system, I don't need to copy package from kernel space to user space, and then back to the kernel space. I process them directly in the kernel space, which significantly reduce latency. And finally, I reduce the jitter in both RTT and throughput. And here's my reference. I refer about 16 paper. So thank you for listening.